Hello, Professor Sargent here with you again. We're continuing our discussion on section 7.3 using the product and quotient rules for radicals. And let's not also forget that we have this relation of the nth root of a raised to the nth power equals a to the power m over n. That's if the nth root of a exists. If you have an odd index, no problem. But if it's an even index, then you better have a positive number underneath as the radicand. So notice in our directions here that we're going to assume that whatever's put in for variable is non-negative. Well, positive, non-negative allows for 0 as well. So we've got our product rule and our quotient rule for radicals. Remember, with the quotient rule, it's implying division. We can't divide by 0. And one more thing I'm going to add here is that when we're asked to simplify, whatever the index of the root is, we don't want any perfect nth factors underneath and nth roots. No perfect nth factors under it and nth roots. Now, there's a variety of ways that we could find the largest perfect nth factor of something. We could discuss other options in class, but for the sake of the video, I'm going to go the quickest that I can. With number 1, both 16 and x to the 6th are perfect squares because square root of 16 is 4. And remember, although it's not written, the index of a square root is 2. So if we applied the connection of radicals to rational exponents, then we would divide the power of 6 by the index of 2 to get 4x cubed. Another square root in number 2, and yes, the power there is also even. However, 20 is not a perfect square. There's a lot of ways we could break down 20, but the largest perfect square that goes into 20 is 4. Since t squared, that exponent is a multiple of the exponent. It's a perfect square. I'm going to break up 20t squared as 4t squared times 5. Then apply the product rule. Square root of 4 is 2. Square root of t squared, we're dividing that exponent by the index of 2. And the 5, here I can see that there's no perfect square other than 1 that goes into 5, so I made the right choice that 4 was the largest perfect square to go into 20. 64 is a perfect 6th power. It is 2 to the 6th. So if you'd like to see a little more written here to help out, as for the y to the 12th, another way we could look at that is that because the index is 6, way to come up with y to the 12th is y squared must have been raised to the 6th power with those exponents right next to each other. That's not y squared times y to the 6th. That's y squared to the 6th. Multiply those exponents, we'd be back to y to the 12th. That negative was in front. It's a -1 times, it's tagging along. And then the 6th root is going to cancel those 6th powers. You can apply similar thinking back here if you need to. Now, since 32 is 2 to the 5th, 1 over 32 is 1/2 to the 5th power. 60 is 12 times 5. So b to the 60th, we could get b to the 12th, then to the 5th power. And similarly, with that power of 55 on C, 11 times 5 will do the job. So that 5th root is canceling out all of those 5th powers. 1/2 of b to the 12th, c to the 11th. More variables on this one, but their exponents are all multiples of the index of 3. And 64. 64 is 4 cubed. Negative 64. Notice we've got a negative outside and a negative inside. Negative 64 is negative 4 cubed. A to the 18th is a6. A to the 6th cubed. B to the 12th is b to the 4th cubed. And c to the 6th is c squared cubed. In all those cases, if you multiply those exponents that are right next to each other, we'd be back to where we started. And so the cube root is going to cancel out all of those powers of 3. And then the negative times the negative, once we've got rid of the roots, those will cancel out in this case. So we get 4, a to the 6th, b to the 4th, c squared. Back to a square roots. Now we get into something a little more interesting. 32 is not a perfect square. We can handle that similarly to what we did with the 20 back here, but also x to the 7th. 7 is not a power of, not a multiple of the index of 2. So, I'm not going to show this a lot, but square root of x to the 7th, if I just look at that part, using this fact, is equal to x to the 7/2. 7/2 as a mixed number is 3.5. 3.5 really means 3 plus 1/2. So that's equal to x cubed times x to the 1/2, which when we go back to writing it with a radical is x cubed times square root of x. How could I write that similar to what I was doing in 3, 4, and 5? Well, that negative's out in front. The largest perfect square to go into 16, into 32 is 16. It goes in twice. The largest perfect square that is a factor of x to the 7th is x to the 6th. Because the index is 2, I'm looking for a multiple of 2 that is the closest to 7, but less than it. And we would have to multiply x to the 6th by x to the 1st to be back to that x to the 7th. So I write the 16 as 4 squared, the x to the 6th as x cubed squared, and then the 2x. Apply the product rule, and it's going to cancel the squaring on the 4. The squaring of the x cubed, but that 2x is still underneath a square root. So we get negative 4x cubed times the square root of 2x. And if you look at what I had here, regarding just the x's, I had an x cubed on the outside and an x to the 1st inside. Same result for just the x's. So that's something that you could use as an alternate approach, but in the end, if there's any fractional exponent, you need to go back to writing it as a radical expression. And if you have a few floating around, you'd have to combine those things that you could not simplify the root any further. You'd have to put them back together under a single root. All right. I'm going to erase what I just did in a moment so that I have a little more room to write for 7 and 8. Here we go. All right. 320 is underneath the 6th root. I could break that down as 32 times 10. And I mentioned earlier that 32 is equal to 2 to the 5th. But we don't have a 5th root, we have a 6th root. But 10 breaks down into 2 times 5. So 320, if we combine those 2's, we really have 2 to the 6th times 5. In other words, 64 times 5. 64 is a perfect 6th power. Now, as for the 16, the closest multiple of 6 to 16 that is also less than it is 12. Still have that 5. And to get y to the 16th, I would have to multiply y to the 12th by y to the 4th. So we could write y to the 12th as y squared to the 6th power. Apply the product rule. And the 6th power and the 6th root will cancel out there. We're just left with 2. Cancel out here. We're just left with y squared. And in this part, not only is there no perfect 6th power except 1 to the 6th, which is 1, there's also no perfect 6th power that would go into y to the 4th. I know that because that exponent is less than the index. Be careful how you write that and how you type it in on MyLab. That 2 is a power of y, whereas that 6 is an index of 5y to the 4th. All right, and one other thing. Again, I said I would not show this very often, but I will do this one more time. We could have taken that 6th root of y to the 16th, written that as y to the 16 over 6. 6 goes in to 16 twice with a remainder of 4. So that's 2 and plus 4, 6. So what do I have here? I've got the y squared outside and then the y to the 4 6th. I see that got converted back to a 6th root of y to the 4th, and it's trapped underneath the 6th root, just like the 5 is. All right, just a few more. On number 8 here, 160. It ends in 0. 16 times 10. I'm actually going to get to use the same kind of thing I did on the last one. 16 is 2 to the 4th. 10 is 2 times 5. So I get the 160 is 2 to the 5th times 5. And so that's good because we've got a fifth root and 2 is being raised to the fifth power. So with the 2 to the fifth at the beginning, 5 at the end, fifth root there. 59 is not a multiple of 5. The closest multiple to 59, the closest multiple of 5 to 59 that is less than it is 55. And for C, not a 54, not a multiple of 5. 50 is the closest that is less than it. So I'd have to multiply b to the 55th by b to the 4th to get that b to the 59th, and c to the 50th by c to the 4th to get that c to the 54th. Do a little erasing again. So applying the rule and taking the product rule and taking the fifth root of what we can. 55 is 11 times 5. 50 is 10 times 5. And we've got this part where 5, the only perfect fifth power that goes into it is 1. These exponents are too low. Cancel out the fifth root and the fifth power. We've got 2, b to the 11th, c to the 10th, and then this part trapped underneath. Fifth root of 5, b to the 4th, c to the 4th. 2 more of this type, and then I'm going to show 2 more examples related. Okay, we've got the square root of x to the 7th over 16. That's all underneath the square roots. And 16 is a perfect square. I'm first applying the quotient rule, and then we already saw, although I've erased it now, what happened to x to the 7th. I wrote that as x times 6 times x to the 1st. We could write x to the 6th as x cubed squared. So when I applied the product rule in the numerator, divide the power of 6 by the index of 2, we got x cubed square root of x all over 4. And if you either wrote down some notes or if you rewind, you should see that back here we had an x cubed outside and an x to the 1st inside. All right, last one of this type. 2 possible approaches. (22) is not a multiple of 10, but the closest multiple of 10 to 22, which is less than it, is 20. So 22 is 20 plus 2. Go backwards instead of saying that we're multiplying these and then adding the exponents because we have the same base. I'm going the other direction. Apply the product rule. These are 10th roots. 10th root, 10th root, 10th root, 10th root, and 10th roots. Got to make sure by the end that we've got that written everywhere it applies. Okay, so divide the exponent of 20 by 10. Got an x squared that's completely outside of a 10th root now. And as for the last parts, I tried out a similar question on my lab, and they did what I expected. I don't know if they would accept this. So what I did was I thought of this as 2 over 10. In this case, I reduced the 2 over 10 to 1/5, and then I converted it back. x squared to the 5th root of x. The other option would have been perhaps quicker. Rewrite that as x to the 22 over 10. Reduce. Divide top and bottom by 2. 5 goes into 11 twice with a remainder of 1. So 11/5 is 2 plus 1/5. So we've got x squared times x to the 1/5. That's back to this. And so we could write that final answer of x squared, 5th root of x. I want you to notice something if I have it still up there. Give me a moment to check if it's still up there. Oh, it looks like it's one of the things I erased apparently. Okay. All right, we're going to look at 2 more examples, something that's related. Not exactly the same, but related. Here we are asked for the unknown length in a right triangle and, if possible, simplify the answer, which probably at most for these questions would involve using the product rule. So to remind you, we have a formula from the Pythagorean Theorem which says that a squared plus b squared is equal to c squared. There's actually more to that. First of all, it only applies for right triangles, meaning we have a 90-degree angle. A and B, it doesn't matter which one gets labeled this way, but we call those the lengths of the sides, called the legs of the right triangle. Together they meet up at the right angle. And then C is the length of the hypotenuse. It is always across from the right angle, and it is the longest side. Maybe that's why they say it's the hypotenuse. Seriously, that's not a joke. All right, so in our question, we were given the following. Let's see here, share it again. We have 5 and 12 for legs. Doesn't matter where I put them, because when I do the work according to the order of operations, squaring and then adding, 12 squared plus 5 squared would be the same thing. So exponents first, and then add. Technically, as we discussed at the beginning of the chapter, there are 2 solutions to that equation. Both 13 and negative 13 are square roots of 169, but we agreed to talk about the principal or positive square roots. And since 169 is a perfect square, its square root is 13. That is the length of the hypotenuse. So I'm going to type that in so you can see that I have it correct. And then it goes to another Pythagorean theorem question. But this time, we're given the length of the hypotenuse and one of the legs, and we have to solve for the other leg. So we're solving for B. We're going to put in 5 for A. We don't know B. And the hypotenuse is labeled with a length of 17. I'm going to try to do this from memory. I believe that 17 times 17 is 289. Let's do a quick double check. Let's see, 9 carry a 4. that went too far. There we go. Yep, 289. So subtract 25 from both sides to get b squared alone. That's going to give us 264, which is not a perfect square, but we erase this part. It is even. So let's see how many times I could divide 264 by 2. 132, that's still even. That's going to give me 66. That's still even. 33. The 3 will go into that 11 times. 3 and 11 are both prime. So what I'm going to do is write this as 4 times 66 and apply the product rule for radicals. Square root of 4 is 2, and the 66, I'm claiming that since I didn't have enough more copies of 2, let alone enough copies of 3 or 11, I won't be able to go any further with that. So let's see if my lab agrees on that with an answer of 2 times the square root of 66. All right. 2, you don't actually have to type the time sign, 2 square root of 66. And they liked it. All right. That's all I've got for section 7.3 for now. Hope it helps, and I'll see you in class. Stay safe and healthy.